the Engagement Manager here at America Makes, and I will be your host for today's TRX webinar presentation. A little background on the TRX webinar series before we introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting in the TRX webinar series, there will be a link in the chat with the request form to present. Go ahead and fill that out if you would like to be on the list for presenting. I believe we are booked through 2024, so it will be 2025 that we begin looking at here shortly. One important thing to note before we kick this off, at the end of the presentation, there will be an opportunity for a Q&A session. At that time, if you have any questions that you'd like to ask, I would request that you come off mute and have some open dialogue with our presenters. Usually provokes more questions, more engagement from those that are participating. And if you don't want to come off mute and ask directly, you are welcome to put your questions in the chat. So with that, today's presentation is titled 3D Printed Chemically Resistant Masks for Electroplating MRO. And masking of metal parts in preparation for industrial electroplating and aircraft MRO involves labor-intensive, expensive, hazardous, and wasteful manual tasks, and is a process that is overdue for modernization. Additive manufacturing of masks for MRO is a great solution, but existing polymer AM materials lack the combination of chemical, heat, and impact resistance needed to withstand the extreme environment of an aerospace plating bath. Figure Engineering has developed a purpose-built AM polymer and process for this application and is delivering the material on a scalable, modular, accessible platform via Formlabs MSLA printers. This webinar will discuss both the challenges encountered and overcome during the years of development, as well as the exciting production, implementation path ahead. Let's see. So now it is my pleasure to introduce our presenters for today. First, we have Chris Crowley. Chris is the Director of Formlabs Federal, focusing on contracts and support for the U.S. Departments of Defense and Energy, as well as NASA, Homeland Security, and overseeing business with all major aerospace and defense suppliers. Chris brings the unique requirement of these customers to the Formlabs product and customer teams to help position the company for further growth and adoption of an already substantial market share and install base in the industry. Presenting alongside Chris is Jonathan McDaniels of Figure Engineering, and Jonathan has 20 years of experience in development engineering for advanced manufacturing. He has worked in the aerospace, defense, chemical, and semiconductor industries on projects such as photopolymer formulation, material development, automation, sensors, and microfabrication. A key area of focus has been on the development of materials for use in aggressive chemical and industrial environments. Jonathan directs the technical operations at Figure Engineering and manages the company's government and commercial project portfolios. Now, I'd like to turn it over to Chris and Jonathan for their presentation. So go ahead, Chris. Take over.
Thank you, Zane. So today we'll be covering just a sound check. You guys can hear me clearly. I'll just wait for one nod. Are we good to go on that?
We are good to go.
Okay, excellent. So yeah, today we'll be presenting. I mean, the abstract kind of did us some pretty good service there. It was a robust one. Really a teeny part, but I would think most pilots would agree a very important part of the aircraft is going to be covered. How the technology we're talking about has mainly been focused and designed on maintaining landing gear, but we'll be talking about 3D printed chemically resistant masks. As mentioned before, I'll be presenting actually really more of an introduction. Jonathan really did the brunt of the technical work here on this. And I hope to turn it over to him fairly quickly because I think he's got a lot more interesting things to say than I do. It's just my opinion, though. Hopefully you find this portion as well interesting. So what we're going to do, we will talk about low-hanging fruit in terms of additive utilization in aerospace and defense, and kind of reframing how we look at that, why Formlabs exists, and kind of a little bit of a shift in focus for us as a company, and something I want to make sure I communicate that all additive manufacturing people should take note of. how to effectively collaborate to advance additive technology. I think it's really important that we collaborate as an industry. It's an unusually collaborative industry to begin with, but we need to do it the right way. We'll talk, Jonathan will go into the actual technical problems that presented the need for this actual material and process, and then the development of the solution, which is resist resin, which is essentially going to be a commercially available product within the next few months. That'll be used and available to anybody else who wants to use it, but in a specific application to start. And then also the business case. Why did we do this? Why is it just, it's not just a problem to solve, it actually it should have some impact, and how you can actually make it a little bit more robust and useful, not just in the one customer it was designed for, but everybody else as well. And we'll give you a chance to ask questions at the end. So first off, I think it's really important to focus. We do spend a lot of time and energy as an industry working on printed part certification and metal additive manufacturing, which is really hard. It has a really high impact, but there's so much that can be done with polymer additive manufacturing, both in part production and maintenance, where we haven't really realized it. The technology is so there, it's ready for a lot of things to be done if we just focus on making it kind of more purpose-built for a specific application. Not everything has to be ULTEM. There's so many other polymers that are there and useful. And I think it's important that we start to shift our focus from just 3D printing end-use parts, which is really challenging to do. As everybody knows, 3D printing is kind of hard to do. So we definitely want to try to focus on places where we can use additive, where the certification burden isn't so high. There is a lot of things to do in jigs, fixtures, maintenance, aids, and masking is what we'll be talking about today, more really in focus. But there's a lot of places where we could validate a process or a mechanism of utilizing 3D printing in maintenance and production, where we're not literally printing the parts. Scaling 3D printing is arguably just as hard as printing your first product, because it's really hard to use the entire build area, or it's hard to run lots and lots of machines, or machines wear down in a way that is hard to predict. So I think focusing on maintenance enablement, which we're talking about here today, is a really good area for us to get some immediate ROI on using 3D printing. And this statement, look for tape, it comes from a really well-known additive manufacturing SME in the Navy. He was actually referring to the idea of looking for tape where things are literally duct taped together. But anytime someone is bonding two parts together or covering a part with tape, presents an awesome opportunity for additive manufacturing. Tape is made of polymer, so we know that we can replace that material with polymer of one type or another. And also, tape is a 2D thing. It requires a new application. It leaves behind residue, and it has to be disposed of if it's a one-time use thing. So if we can replace some tape things with 3D printed parts, in this one we're talking about masking tape, like fiberglass tape that's used in masking. But there's lots of paint masking and all sorts of other places that tape is used that we could replace it with polymers. And I've also noticed that as we talk to customers about the way they want to use 3D printing, sometimes we can kind of shift our focus from, hey, how do I make this part cheaper from a materials perspective? It's much more impactful, I think, to the industry to make the parts show up faster, to develop it sooner, to make more of them here, not have to ship the parts around, bring them closer to the point of need, make them in the shop where they're needed. This is a big thing we'll touch on today. And not necessarily focusing on the cost of the material itself, but how much value it improves and how fast we can get aircraft back in the air and our products updated and modernized faster. So what I mean by when the AM part is not the product. Top left, this is actually, as you can see there, this is from a Navy location. Honestly, I don't know what they were trying to do there with that stapler. I don't know what the solution was here. But either way, the thing was duct taped together. And this was a place where someone was asked to basically create an additive solution to create a better fixture there. Another one is just basically cable stays and tie downs, where you need to keep things in the right place. This does not need to be a machined aluminum. It doesn't need to be ULTEM. You just need a thing that might have a funky geometry, and that you only need 10 or even 100 of, and the part doesn't exist. That's not that product is that whole thing that the assembly of the wires going in. We're 3D printing something to make that work better. Holsters and work aids that you see there is another great place where you could say, like, well, we have flight maintainers dropping stuff, doing unsafe things to hang on to stuff, or having basically a lack of ergonomics in what they're doing in moving tasks around. I've even seen people print jigs to just locating jigs to put a wheel back on an F-16 aircraft, where there's really useful technology we can do that, where it's like we're not printing the F-16 part, we're printing a part that makes the maintainer's life easier. And cable winding spools on the bottom left, the blue parts, those are additively manufactured. This is for a Boeing supplier, basically a center of excellence in the UK that supplies for Airbus. They have 5 or 6 different applications where they're using 3D printed fixtures or holders or manufacturing aids that break, don't need to be metal, are hard to get, aren't getting made anymore. Bottom center, that's an industrial commercial farming drone, unmanned aerial system. That drone is not even their product. The data it collects is the product. And they have new sensors, cameras, and pieces of equipment that get attached to the drone. And those are changing a lot faster than that drone body is. And so they need to be able to make fixtures to adapt those things on there and just basically affix them to them. And those OEMs don't work together. Like the person who makes the drone doesn't make the camera, they don't make the sensor or whatever they're putting on there. And we need to integrate new payloads. So that's another great example. I was like, I don't make this, I need something to help what I make work better. And the bottom right is just straight up blow molding tooling. That's a Unilever bottle. That's like the same kind of bottle you would get out of your like Dawn dish soap or whatever. And there, that white insert there is an additively manufactured part. It's made of this same resin that I have right here. This I can just actually switch to my main view here. This like coin is just printed in that same stuff. This that material can be used in industrial tooling applications, including injection molding and things like that. So another place where additive can make a benefit, where like I do need my plastic to be a thermoplastic, but I can use a thermoset polymer on a $4,000 printer and actually manufacture and use tooling. So why does Formlabs exist? Honestly, our whole goal since we became around was just to make more accessible, on an order of magnitude, more accessible systems in every way. Cost, complexity, how big they are, how much power they require, the difficulty of operator use. We make smaller format resin printers that are right behind me, the Form 4 printer, and then a larger version of the resin printer, the Form 3L. We also make the post-processing systems that go with them. On the right is our SLS polymer system, which can do nylon, polypropylene, TPU, and a bunch of different materials. So what we try to do is simplify 3D printing. So we want to simplify it. When you have your CAD file, you have your STL file, how do you get to that finished part? From an AM perspective, like post-processing, we make the software that makes it push button, easy to use, and also it has a lot of expert controls on it so that we can actually make the pre-print software really easy. Our hardware is a fully integrated, everything has settings tied in together. We want to remove the complexity of people having to twist knobs and turn buttons just to make a part come out, and then also integrate from one supplier, washing, curing, all the things that you would need to actually make the part ready to use. And materials. So we're a materials manufacturer. We make our own materials. We design them. We make them here in Ohio. We design them here in Boston, where I am, in Somerville. We manufacture them at our facility in Spectrum, which we'll touch on later, in Ohio. And we want the widest variety possible and the most useful materials on the market. But what does that actually lead to? We want software that makes it someone who doesn't know how to use it. For example, someone in a maintenance shop where they're learning to use electroplating masks, we don't want it to have to be that they have an AM technician or an AM SME on site. We want them to be able to push button and set up a job to be able to print it, or a war fighter in a deployed solution situation, or an innovator in an innovation lab who's never touched a 3D printing before. But we also want the people who are expert users to be able to tweak and turn knobs that they need to get the optimal performance out of it, and design parts for additive, things like that, where they can actually make it work really well. Our hardware, we go for reliability and scalability so that our printer works. If you have 50 of them, they work the same as if you had one of them, and they're small and compact. And when you push this button, it's really important to know that it's not going to be a finicky thing. This platform we develop is supposed to be basically push button. And we sought first as a company to make an off-the-shelf system that you know can work every time. And I think that's really important in this scenario where we are basically, Jonathan is used an open version of our materials, our software for print preparation to actually tweak and introduce a new material. It is so much easier to do that when you know the backbone of the printing technology will work. If I push the button on this thing, it's going to work. So if I start working with exotic or funky materials, I need to know that when I start changing my formulation or changing things, the print platform I'm working on, that I understand fully and can use really easily, so I can reduce the variables. And open materials mode is basically a way to use our printers and go into new development. And we really hope that more companies like Jonathan's can start to use and integrate other 3D printing materials and develop new things. And just a little bit of a change from us. So I understand if there's like maybe some questions about how Formlabs typically have been like pretty proprietary and closed in system. We definitely have a lot of potential in industrial applications when people can make things purpose built for what they're doing rather than just using our off-the-shelf stuff. So moving on from that into how did this technology and our collaboration work? I think it's a model, to not be self-centered. I think that there's a lot of things for other suppliers of hardware and materials and R&D and customers to think about when they're collaborating. I use two images here as a little bit silly. Top right, this is what collaboration should look like. There should be someone who does something really well, and then there should be someone who does something else really well, and they can work together to make like a better forward mission, right? Like that big supply vehicle is different from that fighter craft, and that fighter craft can go further because it worked with that. So as opposed to 3 prime vendors fighting over what they want to do, or 5 government customers all who have the same problem and none of which have the expertise to do it, it should not look like the Spider-Man meme. It should look more like the top right. So it's really important to have multidisciplinary expertise on both sides of the equation. So make sure that you try to find a company or an R&D project or a customer to work with who understands the entirety of the ecosystem and isn't coming in with this super microscopic view of what they're working on and doesn't have context of the business of your business or the business they're helping with. Another big benefit that we saw with working with Figure Engineering was that we had a lot of really good overlap in who we were talking to. Jonathan and I knew lots of people at the depot, the Air Force depot we were talking to, but they didn't know we knew each other, and they had never thought of putting us together before until we basically joined forces through a little bit of networking. And that's really important because people tend to think of suppliers in a narrow context, like we're an off-the-shelf printer and material manufacturer. You wouldn't think we were capable of materials development of a novel material because it didn't seem like that. We collaborated with Jonathan, who just had excellent performance in unrelated topics, like things that we weren't working on and you wouldn't think of, but it's actually a really good partnership. And Jonathan's whole team knew everything about polymer chemistry and new development. And then both had relevant past performance. So, we having understanding of the industry. Why would someone care about electroplating MRO? Why is it aerospace MRO such an important and large scale opportunity? We knew that, but Jonathan had more exposure to actually working with those depots and dealing with the hazmat. Like I had no idea that chrome plating was so common. I had heard of nickel and copper plating for antenna and R&D use. I had no idea how common and how much plating they had to do, and also how toxic the waste output was. That wasn't even on my radar because why would I know? I've seen Aaron Brockovich, and I knew that hexavalent chromium is dangerous, but I didn't know how much of it they were dealing with. And as Jonathan and I have explored a few projects, and I bring this to other companies too, it's kind of a red flag to me when people are saying like, oh, I want to use your 3D printers to just gain that capability for the art of the possible. We don't even know what we want to do. I use this word like the art of the possible. I think the edge of what's possible is much more interesting. So we had seen people who had highly chemically resistant resins. We have that. This resin I'm holding right now is highly chemically resistant, but it's brittle. And highly durable materials that weren't brittle were not very chemically resistant. Jonathan will touch on that more later. But we wanted to go to the edge of what no one had done before and make something that just needed a little more to be purpose-built for what they're doing. This shortens the curve to actually doing something interesting with a 3D printer, is saying not what's a pie in the sky thing. Like, for example, printing prescription eyewear that can meet ballistic standards downrange. Those are like dreamer topics. We like to go to things where it's like we're so close, if we just push it over the edge, then with a little bit of time and effort for a purpose-built thing for the aerospace or even just like a government customer specifically, then we'll actually be able to accomplish something in a short period of time. And most importantly, I think, is that both companies, all companies involved, the customers, we had a lot of like so much respect for the government customers that are respectful of our companies. We have to stay in business. We have to understand the risk to the company when there's a lack of funding or time and availability to just go chase basically a shiny object, like something new, like, oh, you could do this with our printers. Formlabs does not have time to go develop niche materials like this because we focus on globally off-the-shelf relevant materials. Figure Engineering, they can chase this down, but only if they can basically get their funding opportunity funded by things like SBIR or matching funds to actually take it to implementation. And we're a big company, so we have people working on a lot of different things that take a lot of time. We had to divert resources towards this one. So we had to be transparent and focus on what we're really good at. We are good at making lots of resin, making resin work really well, repeatedly, above 90% print success rate on our printers. But what we're not good at doing is chasing down random aerospace requirements for materials and getting into plating shops. I've been to this plating shop we're talking about, but 99% of Formlabs doesn't even have context on what we're doing. So you really, when you collaborate with another company, you need to be kind of transparent and not hold the cards on saying, I can't divert my material scientist time to help you with this because they are busy right now. Sometimes there's a window, like an America Makes project call, and there's a 30-day window basically to get a proposal in. You got to have people ready for that and manage expectations of how you're going to have people like propose things and understand that your partner has to be able to do what you're not capable of. Writing SBIR proposals, Jonathan's team is really good at that. Formlab's not even a small business. We literally can't do that. So we stick to what we're doing best, and I think everybody should try to do that when they're coming into a collaboration. So with that said, I think we were a good platform for which Jonathan could use and develop his technology for. Here, his company really did the hard part of the work with this, which is figuring it out and doing it. And I have just been so impressed by the whole team at Figure Engineering, Jonathan and his material scientist, Gabe, who I think is on the call here, but helped with this a lot. The Figure Engineering has terrific past performance in things way outside what we're showing here, everything from personnel decontamination unit, deployability to basically solving robotics problems, and even, I shouldn't say like maskless paint things. They've been awarded some really cool projects that have nothing to do with 3D printing. I've just been blown away by their ability to basically understand what we work on and speak the same languages as our material scientists. That blew me away only because they had done so many other things. So Jonathan is a super smart guy. I'm going to toss the presentation over to him now for him to take it from here. And as he does that, I'm actually just for fun, I'm going to start a print on this Form 4 while he's talking, and we can see if we can pull off that print by the time he's done. So Zane, if you want to transfer the control of the presentation over to Jonathan, I'm going to go and just walk over here and get started on this printer while we go.
Absolutely. Jonathan, you are good to go.
Yeah, let's see how we're doing here. All right, so got the slides up?
Yep, you are ready and set.
All right, perfect. Thanks a lot for that introduction, Chris. It's always nice to, it's really kind words from you, so we definitely appreciate that. My name is Jonathan McDaniels. I'm the Chief Scientist at Figure Engineering. Figure Engineering is an advanced manufacturing and sustainment technology company. We do a lot of research and development in maintenance, repair, and overhaul. Core areas of focus are in new material developments, robotics and automation, and industrial health and safety, particularly with hexavalent chromium, which Chris alluded to as cancer-causing, highly toxic material. One of the things that we really focus on, we call the 3Ds, dirty, dull, and dangerous. You see it a lot in sustainment and manufacturing operations. These types of processes, these types of jobs, people don't like doing. They're labor intensive, they're time consuming, they're dangerous. We like to find solutions that can remove people from these processes so they can focus on things that are more engaging, safer, better uses of their time. So one of these areas is masking for electroplating. So just a little bit of background on electroplating. Electroplated coatings are used in a lot of different industries. They're used for corrosion control, thermal resistance, impact protection, say from like on a landing gear, say, rocks or other debris getting kicked up and striking the landing gear components. They're used for dimensional restoration. In aerospace, a lot of components, like engine components, are used for protection from thermal or corrosion. In order to have a successful plating process, you need to use masking to allow the metal to be placed where you want it and block metal from being deposited where you don't. There's a lot of different ways that this has been done in the past. Going back to what Chris said about look for tape, this is a perfect example because tape is used heavily in this process. You have hand applied tapes that are precisely laid in by hand. You have waxes and lacquers that are hand painted or dipped, and then you also, for a longer term, more robust solution, you can go with machined CPVC. The downside of that is that you have a bit of a high upfront cost. One of the big challenges with the legacy methods of masking are that they're expensive and time consuming. These waxes, lacquers, and tapes, they're, like I said, they're hand applied, so they are skilled, labor intensive. If they're not applied correctly, that part ends up being scrapped. If you miss a spot or you have a hole or you cover an area you didn't mean to cover, they are one-time use. You paint it, you tape it, you put it in the plating process, it comes out, you strip that off, and it's gone. All of that work is gone. And then even worse, that tape or that wax that you removed, if it's gone into a chrome electroplating process, it's disposed of as hazardous waste. So there's a lot of issues with waxes, lacquers, and tapes. Like I said, one of the more robust and repeatable methods that's sometimes used to alleviate this is machined CPVC. Main drawbacks to CPVC are the high cost of machining with CPVC. So, for example, this part, which is about the size of, I'd say like a softball, is about $2,000 to have machined. But even something that's small and handheld, like this pump housing mask, is $250 a piece. Entire assembly sets of CPVC can be upwards of $4,000 for a set. Lead time, we're talking 6 weeks to have something made. So if you've got an operation where you have high variability workload, CPVC is really not feasible for you because the costs are so high and the lead times are so long that a lot of times what we've seen in commercial plating shops is if they have parts come in that have somewhere over 30% of more than 30% of their surface requiring masking, they will actually turn down the job. Air Force doesn't really have that luxury. Like a part comes in, they got to do it. So they have to make it work, no matter how expensive it is. One of the reasons they're asking for additive manufactured masking. So brings the advantages of additive manufactured masks. It's really the logical solution to address a lot of these issues. 3D printed masks have the reusability. They have the repeatability. It's the same mask every time. It's going on the same spot. You don't have to worry about something like a pinhole or something extra being put on there. It's the same part every time. They can be printed for far lower cost than something that's machined out of CPVC. They don't require the skilled labor that's needed for your hand-applied waxes and tapes. And as for part availability, you can have something printed and ready for use in a few hours instead of 6 weeks. It's the main reason that we created Resist. So we worked with the Air Force under the SBIR program to create a tough, chemically resistant material that could be used for electroplated masking. We'll talk more about the development that we did in some of the later slides. But a quick overview of what is required to use Resist. When we went into this, it was basically a blank slate. So the Air Force wanted a material. They wanted a printing process. There's a lot of different ways that could be done. From our perspective, we're good at developing the material. I didn't want to get involved in trying to develop a printer. I didn't want to go with printers that were complex, unreliable. Formlabs was a perfect partner to look for on this because, like Chris said, their printers are easily accessible, they're easy to use, they're high reliability. The cost per printer, it's not going to bankrupt you. You can, and some of these plating shops run really tight on budget, so it's a lot easier to buy a line of form printers and wash and cure stations than it is to say some of the other companies that are producing equipment. So required equipment, we're working with Form 4, Wash L, Cure L. The Resist, we're working on a scale up for manufacturing with Formlabs. There aren't any special requirements for post-processing. It's mainly support removal if you need to sand it or clean something up. That's simple enough to do. And the wash solvent, we found that odorless mineral spirits is a good wash for this. So it's got lower flammability than say like your IPA. It works really well for this material. Quick overview of the material properties. I'm not going to dwell on this slide for too long. I just want to point out the notched IZOD at 44.1. Like we said, we need high impact resistance for this material. And then over here in the chrome plating, low chemical attack. So talking a little bit about the developments of the resist material. Electroplating is a really chemically aggressive environment. You have high temperatures, you have acid or alkali solutions. You also, because it's a plating shop environment, you've got people that you've got large landing gear parts moving around there. You've got people, you can drop these masks. You have something that maybe doesn't fit exactly right, and the people in the shop are going to knock it into place with a hammer. So you really cannot have something that is brittle. And like Chris said, there's a lot of materials out there that have good chemical resistance, but they're brittle. So that was one of the major things, and we'll talk about that. The requirements we set out to meet at the beginning, you need to have no porosity. If you have porosity, it's going to soak the plating solution up, the toxic plating solution up, and it's going to leach it out. When you're done with the process and you set the mask on a shelf to be used next time, you're going to come back and it's going to have leaked out a bunch of hexavalent chrome all over the place. The mask needs to be chemically resistant, needs to have high impact strength, needs to have low thermal expansion so that when you design a part and you need to have the plated part come out with certain dimensional tolerance, when you put it in the hot liquid of the plating bath, that material can't expand and then mess up the plating. You need to be non-conductive. It needs to have high surface energy, so it's got to be able to bubble shed. These plating baths tend to, when you apply current, generate hydrogen gas at the surface. So that needs to be able to shed away. If it doesn't, you're going to, and you can see some of this in that upper right picture, those bubbles are going to collect, and then that's going to mess up the plating. And then the last requirement is that it does not contaminate the bath. This is really a lot of times unique to electroplating, but a lot of materials that you would use in other processes are big no-nos for electroplating. So like something like a silicone oil or something you might use for, or a plasticizer you might use. If it leaches out, it's going to cause adhesion failures. And then your entire 1,500-gallon plating bath's got to get dumped, and you got to put a brand new one in. So really important that this 3D printed material does not contaminate the bath. In our early stage testing, we found that all commercially available additive materials that we tested did not meet these requirements. So we had to go out and create our own. Our initial work for this development was to screen a large number of formula candidates for chemical resistance performance before we even got it into a printer. Once we had printable formulations, we could get cubes for testing, but we put it in the chrome bath, 24-hour soaks, 5-day dries, looking for color changes, looking for evidence of leaching, weight changes, so that we could kind of screen out the most promising candidates. So like I said, these masks are going to be used in an industrial plating shop. So we found a lot of components that had good chemical resistance. Issue was that most of these were brittle. So we had to thread the needle to find a formulation with excellent chemical resistance while also maintaining that good toughness and impact strength, with our aim to hit 50% of CPVC. Additions to the formulation that aid in printability will harden the material and make it more brittle. So you have to have these things to make it 3D printable, but they negatively impact the performance of the material. So the challenge was to find these tough and flexible replacements to compensate for these necessary additions while also maintaining the chemical resistance. So you can see some examples here of like a good part and then a bad test result, and then say like a catastrophic test result where it just completely disintegrated in the electroplating bath. One of the things we quickly learned during the development was that chemically tough and impact resistant materials really pushed the boundaries of what was possible with both photocurable polymers as well as the 3D printing equipment. So during the development, we needed to continuously run compatibility tests to ensure that the formula components would play well with each other, and that those formula components would also play well with the printer tank. Many good options had to be eliminated because they just didn't work as part of the whole formula, and then others had ratio restrictions. Like I said, on the impact resistance, we're aiming for 50% CPVC before and after, and then multiple cycle testing. The development progress was iterative. So we would screen, we would test compatibility, we'd formulate, find the limitations, and repeat. There were a lot of DOEs performed to fine tune. Each cycle, we would improve the properties of the material. So I can see here it started off fairly soft and flexible, which, while that's That's good for some applications. It was not going to make a good mask. You need to have some stiffness, but you can't have brittleness. So we work to increase the hardness and the stiffness without degrading the impact and the chemical resistance. The other side of the development that was happening at the same time was tuning for printability. Initial work revolved around understanding how our materials would cure in the printer. So we created various in-house tests and experiments to study the effects of the components and how their reaction speeds could allow us to tune for good printability. One of these tests was creation of the working curves to understand the relationship between UV energy exposure and cure depth. Different photo package components affect the curing kinetics differently, so it was important that we kind of lock that down and understood what different things did, so that as we're tuning the formulation, we could also be tuning for reasonably good printability. During the bulk of the development, we're working with Form 3 printers. We purchased multiple material settings editor licenses from Formlabs. MSE worked really well for us for initial development and tuning. It had a good range of settings to adjust. I mean, you always want more settings, but for what it had a lot of really good settings to adjust, and it helped us get printable formulas. Most importantly, though, it gave us the ability to bypass a lot of the guardrails that the printer had, so that we could work with very small amounts of resin, which would allow for rapid screening. MSE helped us a lot during the early to mid stages of the development. When we got as far as we could using MSE, Formlabs stepped in to help us better tune the settings. During our tuning of the printer settings, Formlabs released the Form 4, and this had a major impact on our final development. And like I've said before, because our resist formula was really pushing the boundaries of what a 3D printed material could do, we had a lot of issues with compatibility in the Form 3, which made settings adjustment difficult. So we could get successful prints, but reliability was not where we want it to be for a commercial product. The Form 4 practically overnight fixed a lot of our issues. I was invited to the launch event, and Amar, one of Formlabs material developers, had a bag of parts that he had printed in resist on the Form 4 before I even knew that the Form 4 existed. And he showed them to me, and then a lot of these parts were things that were unprintable before, so it was pretty remarkable. So some of the improvements you can see just on some of these particular parts and images here. In addition, there was a huge time reduction in the printing, on average 60 to 80%. One of the other outstanding challenges we're currently working on is the lack of digital data with most of these masks. So these are really hand-applied works of art. You have technicians going in and to maybe 2D drawings or a process order. They're hand painting where these masks go. So there aren't 3D models. Sometimes there's drawings. Part of the challenge and what we're working on now is working directly with the plating shops to identify good candidates for parts, creating that digital data from scratch. Over the course of the SBI program, we went from candidate screening in 2020 to formulation development and chemical resistance validation over the next couple years, and then this past year we did first article demonstration in production baths with aerospace parts received production qualification from the Air Force. On the business case, looking at the time reductions and the cost reductions and actually putting that into numbers, it's pretty significant. Like you're hand masking half an hour to an hour skilled labor. It's not reusable. It's hexchrome contaminated waste material you're generating from that versus even being conservative on the printing, you can get an 85 to 90% skilled labor reduction. And then on the cost side, like I showed you, these CPVC masks, anywhere from $250 to $2,000 to $4,000 versus something printed with resist. You're seeing 80 to 90, sometimes more reduction in cost. And I'll add that by using Formlabs equipment, your capital expenditures are also not gonna put you in debt when you set up a shop to do this. So, a little bit about the next steps. So where we're at right now, we're working with Formlabs on the final tuning of the print settings. That's going to be done relatively soon. We are starting the manufacturing ramp using Spectra Photopolymers, who's a subsidiary of Formlabs. So we're moving towards commercial product release. We are working with an Air Force customer on technology insertion in the first plating shop. So that's equipment, materials, and conversion of legacy masks into 3D printed files. And then beyond that, once we have a demonstrator set up at an Air Force location, we're going to proliferate to other plating shops with equipment, materials, and printing files, and just build the library from there. So I'll turn it back over to Chris, who can talk a little bit about the work at Spectra Photopolymers.
Great. Zane, would you mind giving me just control back with the webinar? I just have one or two more slides before we go to Q&A. Okay, or the spotlight, yeah. Okay, great.
Absolutely. Yep. Spotlight for you. Yeah. And then Jonathan, if you want to either control for Chris or take down your share, and then Chris, you can share. There you go.
All right. Let's go screen share. Just so everyone knows, that I just printed that part. It's this enclosure right here. It's just done here. Just put it in the wash over there on the same printer Jonathan was just referring to. People, I think, are maybe less known. We actually, in 2019, we bought our material supplier Spectra Photopolymers because basically we were their biggest customer by a long shot. And this gives us an amazing ability to basically in-house develop our formulations and then take them to scale really efficiently. But they actually, Spectra is technically like Formlabs Ohio. This is where our print farm is, with hundreds of printers producing our sample parts. But they make a lot of other things too. The reason I put this slide up here is partly because we are a resin production partner for other companies that make 3D printing materials and others. So we have the ability to scale this manufacturing technology where it figures basically making in very small batches up until now. And one of the main conditions of the Air Force requirement is at the end of this thing, this has to be commercially available off the shelf thing. So if it's not in that state, it's not useful to the Air Force. And one really important thing I want to point out is there's so much ripe fruit on the vine for use in 3D printing in DoD and aerospace applications. We have to pick it and start using it. So walking through just like a summary of what this happened and what has to happen next to actually take advantage of this. I'll call out to the audience as well to get involved or come to us and ask us questions about this. There was a need known is that there was this huge plating need, and that no materials met this, and that they had this labor problem that had to be solved. That off-the-shelf options weren't there, and no 3D printing company was willing to dive in and go further and deeper on this. Figure engineering was with government funding, and that really made it possible. VC, like private funding for these kinds of efforts, these niche applications, especially just aerospace and defense and government, it has dried up so much. They don't want this long-term investment, the high-risk thing, so much riding on one contract. So government funding really made this possible. It's a call out to the actual basically customers, so to speak, of America Makes, who would be benefiting from these kinds of partnerships. Figure Engineering made it work. They actually developed a resin that could do what they needed, and they did the testing and the qualification with the Air Force to actually get them to say, yes, this can be done on production assets. That's huge. That's the first part. But then can we make it so that it can be plug and play, and that people at the shop can do this and not have to worry about basically a printer they want to push into a dumpster 3 years from now because they never got it to work, or some massive investment. We made it repeatable and reliable with our printers, and also our partnership with making this with Figure Engineering allows it scalable. I think it's really important to make an additive solution that is scalable exactly to what you need. How many printers you need? You shouldn't need $1 million printer, because what happens when you get to 101% requirement of that? A small modular solution that can scale to as many shops as you need, as much need individually as a local shop, was really important. Having that combination of an agile company developing and then a company that makes a modular compact format of it, and then also making it so that it works every time and making lots and lots of it, because the demand right now is low because the number of designs that can use this is very low. As that design library scales up, the demand is going to snowball, and it's going to be an area under the curve. As the number of y-axis is parts that can be printed, the area under the curve is the number of parts printed, and the demand for the resin is going to be huge. So we're used to making resin in a teeny amount first and then making tons of it, like most companies are not. And then also making it a reality will be actually the really hard work, is to take a 2D file that's basically wax or tape, engineering drawing, and make it into a 3D printable part. And so that's where a partner like Figure Engineering is so great, because they can offer the engineering and design execution. And then an entity like America Makes is really valuable because it helps us spread the word to folks like you all. Implementation and transferability efforts is really what is going to make the difference on this. Like we're going to design masks. Figure is going to design masks. They're going to work with the Air Force to do that. But depots don't get implementation like R&D funds. We need transferability projects to call for things like this more often, and give the opening to get these processes implemented at the shop. They don't have any 3D printers at the shop right now, and they can't just send everything to the Additive Center of Excellence at the Air Force Base right there, because they're doing all sorts of big mix of other things, and they're not focused on this. Another thing is transferability. There are way more things than just chrome plating, and I've been amazed at Rapid last year, this year, in conversations with other customers in DoD, other branches other than the Air Force, the Army, the Navy for sub maintenance, other plating applications, vehicle maintenance, and even just chemically resistant parts that are needed. We need more people to tell us that we want this, so that we can really make this a more robust material and part of our portfolio, essentially, that we can support at wide scale. It will be available this year. We'll be able to develop it, but making it really perfect and ready for lots of other people, it's going to require, please come to us and ask if this thing would work for you, if we've done some testing, or if you want to test a part, we absolutely can do that. Figure Engineering can produce test parts in this material for you to test in your process and see if it's the same in your cadmium or nickel plating bath or anything you need chemical resistance for. So before we just turn it off to Q&A, I wanted to mention, like, please approach us about this material and ask us how to get it. Or if you have a project who you think could benefit, please just reach out to us, and we'll make sure to make the connections and make it available to you. That's what we do. So with that, I don't know if there are a few questions that had come in over time, or if we have some that we can go to, but we can do that now.
Yeah, so thank you, Chris and Jonathan. We're now going to open up for the attendees to have the Q&A session. So if you have any questions for our presenters, feel free to come off mute and ask directly, or if you don't want to come off mute and share it or voice, you are welcome to put it in the chat.
I have a question. I came in a few minutes late, so if I missed this, just let me know. For sizing, a lot of the electroplating parts that we're looking at will require pretty large masks, things that certainly couldn't be printed on a Form 4. Have you guys experimented much? Like, can you print out multiple parts and use some of the resin to glue them together, or have you guys looked at ways to make larger parts?
Yeah, so that definitely, and we've seen that same question come out of our Air Force customer. We can take this and bond it to create larger parts. We can also use smaller parts as an assembly to make larger parts. In the future, there's the potential to move this into larger printing platforms, and it's something we're actively working on.
Yeah. And as I mentioned, we're a material supplier, and we make photopolymers for other 3D printing companies as well. So if Formlabs never makes a printer that's big enough to fit the part that you're talking about, I do think there's parts so big that they will need to be bonded together no matter what, just because there's no printer that makes a part the size of a C-130 landing gear. So bonding them together is totally possible. You can make watertight parts with this. That's a really good benefit to resin printing. It can be bonded with the resin itself. We introduced the Form 4 and opening the platform, like open mode for our printers, to be the #1 platform that's easy to use, and we want to make it plug and play. But we understand we can't solve every single material and setting and print volume size to print successfully across every application. This is to basically create this resin and this process that we know will work. Whether it's an R&D company developing resins like figure engineering, a Formlabs user who wants fewer bubbles in our clear resin or optically pure parts, a resin company wants to do their own unique materials to this. We want the answer to be yes, we can do that. That answer would extend to, I have a massive printer from another supplier, and it doesn't even matter which one. If it has the ability to cure at this wavelength, or we need a different photo package to be added in, it is possible for that. Right now, the low-hanging fruit, like I said, that we can pick is we can hit a ton of the parts need that do fit in the Form 4 build platform and just a little bit bigger by bonding them together. And obviously, we do make bigger printers too. So the plan would be to make things scale up more easily with the same material, because we have this really great print engine here. This big stack of Form 4 optical system here that we have is pretty powerful, and I think it scales pretty well as well.
Yeah, that's what we've seen is really there's quite a few parts that can be printed with the current sizing. And so that's good to know that for those rare exceptions that it can be bonded and you can make good parts or assemblies. So thanks.
Yeah, thank you, Jason. And I will say that we are coming up on time. You are welcome to continue coming off mute to ask questions. I just want to, before anybody has to leave, I want to say thank you for joining, and thank you our presenters for sharing. But yeah, if you have any questions, please feel free to come off mute and continue asking. Thank you, Jason, for that question. Let me see. Got a couple questions here. Are there any best practices that you have for machining materials?
Okay, so so like I said, the material's been designed for good impact resistance, which means that it's pretty capable when you're machining it. So say you're trying to face a surface, or you're trying to get something that you didn't just put into the 3D model. We've seen like as long as you're not being too aggressive with the speed on and the depth, like say you're lathing it or something, you're not going to see any chipping or any damage to the material. It's pretty easily tappable if you're trying to put a thread in there. We haven't had any issues doing that. Yeah, as far as best practices, like treat it as similar to say you're machining with CPVC. It's gonna probably behave pretty much the same way.
Thank you. See here. Anyone else have any questions? No? Cool. All right. Well, let me see. We are over on time, so I want to thank everybody for coming in here. I'm going to stop the recording and hope everybody have a good rest of your week. If you have any interest in being a presenter in the American Makes TRX webinar series, please feel free to either contact me directly or I will share it in the chat here shortly, the link to fill out the form to be a presenter. Other than that, thank you for coming and hope you have a good rest of your week. We'll see you.
And we'll see you at MMX.
Thank you.
We'll see you guys at MMX.
Yeah, thanks a lot.